Welcome to this explainer. Today we're embarking on a truly awe-inspiring journey into the machines that essentially serve as the invisible, beating heart of our modern world. We're talking about computers. Just to put things into perspective for a second, the smartphone sitting in your pocket right now, it literally has millions of times more memory than the Apollo 11 computer that navigated humans all the way to the moon. It's crazy. Today we're going to completely unpack the evolution and the architecture of these incredible systems, relying entirely on some really fascinating data and historical records. Because if you think about it, we interact with these things from the absolute second we wake up until we go to sleep, but we rarely stop to consider how they actually work or, how they even came to be. So throughout this explainer, we're going to guide you through that massive leap from ancient manual calculating tools to the wildly complex digital networks we rely on today. We'll peek under the hood, demystify the internal components, and organize it all step by step. Let's get started. Okay, let's dive into this. When we hear the word computer, our minds usually jump straight to a laptop on a desk, right? But the reality of computing today spans this extreme, mind-boggling spectrum of price, size, and complexity. On one end, you have these ubiquitous, super simple, single-purpose control systems. I'm talking about everyday things, your car's key fob, your microwave oven, the remote control buried in your couch cushions. But then look at the other extreme. We scale all the way up to massive industrial technology. Think of factories run entirely by industrial robots, or colossal, room-sized supercomputers like the IBM Summit. It's wild to think about, but despite looking totally different and doing completely different jobs, they are absolutely part of the exact same technological family. And this family of tech, it definitely doesn't just exist in isolation. These machines are the core of our general-purpose devices, sure, like your desktop or that smartphone we talked about. But their true, world-changing power is unleashed when they connect to one another. Fundamentally, these machines power the internet. It's an infrastructure linking billions of individual computers and users across the globe simultaneously. The sheer ubiquity of it all is staggering. They aren't just tools anymore. They are literally the foundation of modern global communication, turning billions of isolated processors into one massive interconnected digital web. So, what is it that magically links your microwave to a supercomputer? Let's get into section 1. What exactly is a computer? Defining the core system.
At its most basic, stripped-down level, a computer is just a machine that can be programmed to automatically carry out sequences of arithmetic or logical operations. Honestly, that's computation in a nutshell. Now, modern digital electronic computers take this a huge step further by running generic sets of operations we know as programs. And that's what makes them so incredibly versatile. But when we talk about a computer system, we're actually referring to the whole shebang. A complete system isn't just the physical hardware. It includes the operating system, the software programs, and the peripheral equipment you need for it to actually do something useful for you. Or it can even refer to a linked group of computers functioning together, like a network or a cluster. The big takeaway here is that whether it's a 1940s behemoth taking up an entire warehouse or a sleek modern smartphone right in your hand, the fundamental goal, automatically executing programs' logic, remains exactly the same.
So how did we shrink these systems from warehouse-sized to pocket-sized? Let's check out section 2, the evolution of computation from the abacus to integrated circuits. Let's move to and see how this builds across time. Early on, computers were strictly for math. Ancient societies used simple manual instruments, like the abacus, just to aid in calculations. Then, by the early Industrial Revolution, we started building mechanical devices to automate really long, tedious tasks, like guiding patterns for looms. By the 1930s, we had sophisticated electrical machines doing specialized analog calculations. But the real game changer? That was World War II, bringing the dawn of early digital electronic machines. Think of the 1940s ENIAC, this massive machine taking up an entire room just to do what a cheap plastic calculator does today. This massive leap was fueled by the invention of semiconductor transistors in the 1940s, which then rapidly evolved into monolithic integrated circuits from the 1950s onward. Every single step on this timeline represents a technological advancement that gave us smaller and significantly more efficient circuit designs. Now, what's really interesting here is what happened as we transitioned to those integrated circuits. Computing power absolutely skyrocketed, and it's all thanks to Moore's Law. This was the famous observation that the number of transistors we could cram onto a single circuit was doubling roughly every 2 years. And this wasn't just some minor incremental upgrade. No, this was blistering exponential growth. This rapid shrinking of transistor sizes and the massive multiplication of their numbers led directly to the invention of the microprocessor, which of course sparked the massive microcomputer revolution we saw in the 1970s. And you know that relentless exponential growth driven by Moore's law? It definitely didn't stop in the 1970s. Because transistors became completely microscopic and incredibly cheap to produce, serious computing power started finding its way into everyday consumer products. Eventually, it landed right in the palm of your hand. It fundamentally rewired human industry, global communication, and really our daily lives. It paved the way for what we now look back on as the massive digital revolution that spanned the late 20th and early 21st centuries. Okay, let's slow the pace down for a minute and deconstruct how these modern machines actually work. Section 3. Anatomy of modern computers, peeking under the hood. And this brilliantly illustrates how it all comes together. Think of a computer kind of like a bustling restaurant. On the left side, you've got the kitchen. These are your internal workers. We're talking about processing elements like the CPU, memory chips, and the control unit. They are back there doing all the heavy mathematical lifting and data storage completely out of sight. Then on the right side, completely separate in function, you have the dining room. These are the peripheral devices. It's the external stuff that we, the customers, actually interact with. Keyboards, monitors, and the specialized dual-function touchscreens. Really understanding a computer just means understanding the relationship between the kitchen crunching the data and the dining room feeding and extracting that data. So the crucial point is how the kitchen actually operates. The CPU? That is the brain. It's carrying out the actual arithmetic and logical operations. But it definitely doesn't work alone. It relies heavily on computer memory, typically semiconductor memory chips, to hold onto the data it's actively working on. And finally, you've got the sequencing and control unit. This thing acts exactly like a traffic cop. It has this very clever ability to change the order of operations on the fly, responding to the stored information it receives. It seamlessly directs exactly what the CPU should do next based on the programming. So the information is always flowing in this continuous logical loop. First, it starts with you typing or clicking on an input device, sending your raw data and commands straight into the internal CPU. Next, the processor crunches those numbers and executes the operations. And finally, the processor pushes those results right back out to an output device, like your monitor or a printer, so you can actually see and save what just happened. Oh, and if you're using a modern smartphone or tablet, the touchscreen is seamlessly handling that entire input and output loop at the exact same time on the exact same piece of glass. So we've gone from wooden abacuses to massive rooms filled with glowing vacuum tubes, all the way down to pocket-sized digital supercomputers tied into a global network. We've seen how our input flows to a microscopic CPU and outputs to brilliant displays. But considering the relentless pace of Moore's law and the exponential shrinking of transistors we explored today, it really forces us to look forward, doesn't it? With this technology accelerating so incredibly fast, what will the computer of tomorrow even look like? Will it be something we wear, something baked into the walls of our homes, or maybe something so small we can't even see it? Thank you so much for joining me on this explainer to explore the amazing architecture and evolution of the machines that quite literally run our world. Keep questioning and keep learning.